All right, so far we've been doing a lot of simplifying. Today we're going to solve, because there's an equal sign. Okay, so we're looking for the zeros, which are, when we're graphing, it's going to be where they hit the x-axis. And one way to do that is by factoring. So if you look at example 1 here, when we're factoring, you should always look for a greatest common factor first, which I see that these are all divisible by 3, and they all have at least x to the third power. So if we factor out the 3x to the third power, 3x to the third, I need 3x to the fifth, so that would be times 1x to the second. For the 18x to the fourth, 3 times 6 is 18, x to the third times x is x to the fourth, and then for the last one, 3 times 9 is 27, and we already have the x to the third. So here's what we got so far. And again, inside here, that can factor. Factors of 9 that add up to 6 would be 3 and 3. So it would be x plus 3 times x plus 3, which you could rewrite as x plus 3 squared. Cool. So here's the deal. In theory, there's an equation for each part of this. We're like solving the equation 3x to the third equals 0. And we're solving the equation x plus 3 equals 0. You could even say x plus 3 squared. Now here, this 3x to the third. And honestly, we're really just solving 3x equals 0. So you would divide by 3, and you get x equals 0. So anytime you have an x on the outside that's factored out, whether it's being multiplied by a number or not, that x is going to equal 0. If you look at this x plus 3, our one step would be to minus 3. So the way I always frame it in my own mind is I'm always like, oh, it looks like the opposite of what I see. If I see plus 3, it's going to be negative 3. If it said minus 7, it would be positive 7. Here's the other part. It doesn't even talk about multiplicity yet. That comes up later. But essentially they're saying, well, how many times would this 0 happen? And for that, you go to the exponents. If you look, this was x to the third. So they say 0 has a multiplicity of 3 because it was x to the third. This x plus 3, which came out to negative 3, was to the second power. So we have a multiplicity of 2. And again, that comes more into play when we're graphing these problems. So here we go. We're going to solve by factoring. When you're doing that, you got to have it equal to 0, because then we can do that zero product property rule. So we're going to add the 36 to the other side. Now this one's a little strange because usually it's like x squared minus 13x plus 36, which you would make like x minus something times x minus something. The only difference here is we have x to the fourth. So instead of just x minus, it's going to be x squared minus and x squared minus. So we're looking for factors of 36 that add up to 13, which would be 9 and 4. Now, x squared is a perfect square. 9 is a perfect square, and they have a minus in the middle. So that's going to factor still with the difference of squares. So x squared minus 9 would factor to x plus 3 times x minus 3. Same thing with that x squared minus 4. That's another difference of squares, which would factor to x plus 2 times x minus 2. Now nothing in there gets repeated more than once. Everything is different. So everything has a multiplicity of 1. There it is. So here, the x plus 3, that x would equal negative 3. X minus 3, that means x equals positive 3. X plus 2, x equals negative 2. And x minus 2, x equals positive 2. And again, you could set up an equation for each one of those. X minus 2 equals 0, and then add 2, and you still get 2 that way. I'm just saying we're probably to the place where we don't need to actually write the equation. We could just kind of do it in our head a little bit. And again, all of these, nothing had something squared or to the third, so they all have a multiplicity of 1. Which again comes into play when we're graphing. What else we got here? Ooh, 2 for you to try. then we're talking multiplicity. So why don't you pause here, give it a try, and then check in and see if we got the same things. Let's see, 2x to the fourth. A little factor by grouping. They all have a multiplicity of 1. Cool, those are our zeros. All right, so this was a problem we did earlier. You don't need to write it from before, but I think what we had before, let's see, 3x to the third times x squared plus 6x plus 9, which that factored to x plus 3 squared equals 0. So remember with the 3x to the third, we said x equals 0. And then with the x plus 3, we said x equals negative 3. So the negative 3 has a multiplicity of 2 because of the exponent. If you look at the 3x to the third power, 0, we say has a multiplicity of 3. And again, that comes from the exponent. Now if you look at the graph, here it is graphed. It hits negative 3, and it says it has a multiplicity of 2. When it has an even multiplicity, what it does is it hits that 0, and again, zeros are always where it hits the x-axis. So it hits at negative 3, and then it just turns around and heads back in the direction. So when it has even multiplicity, you hit it, and you turn around. Now if you look at 0, that had an odd multiplicity. Now if it just has a multiplicity of 1, it'll just cross right through that number. But if it has an odd multiplicity that isn't 1, there's a weird bend there. So you'll see it kind of goes through 0, and it has like a little like that. So we're going to practice doodling these graphs as well. All right, so here we go. We're going to factor it all completely. Now this has 4 terms, so we're going to factor by grouping. That'd probably be the easiest. If I look at the left side, they have an x squared in common. If I factor out x squared, I'm left with x minus 1. On the right side, my lead coefficient is negative, so I'll take out a negative. 25x and 25 have a 25 in common. So then if we're writing our factors, we have x squared minus 25 as one of them. And the other one is x minus 1. That x squared minus 25 is a difference of squares, so that would factor to x plus 5 times x minus 5. And then you have the x minus 1. So everything in here just shows up once. There's no exponents on it. So they're all going to have a multiplicity of 1. So x equals negative 5. This one, x equals positive 5. And here, x equals 1. Multiplicity of 1. So here's what I do. I make sure that my graph includes all these numbers on the x-axis, the flat one. So I got to go down to at least -5 and at least up to +5. -1, 2, 3, 4, 5. -5. 1, 2, 3, 4, 5. +5. Cool. So it's going to hit at these 3 points, -5, +5, and +1. And the y-intercept is always the only number without an x on it. So it's also going to cross the y-axis at +25. Now you don't need to make 25 little hash marks there. You could just write 25 and give yourself a dot up there. So here's the deal. When you have an odd degree, which this is x to the third, that's odd. Odd degrees start low and they end high, as long as your lead coefficient is positive, which it is here. So we don't need this graph to be exact, but we know that it's going to start low and it's going to end high. So keep that in mind as you go through the points. So we're starting low. We're going to cruise up through our 0 here. We'll hit that 25 and then we'll come down and we'll swoop back up. Now obviously that looks hideous, right? Hideous. But we're good. We're hitting all the right points. You have your zeros, you have your y-intercept, and you have your arrows starting and ending in the correct directions. So odd starts low, ends high. Even, they both start high. And those rules are reversed if your lead coefficient is negative. So let's try a couple more. I forgot how many we have here. All right, we have 2 more to graph, and then you're going to try one out. So if you look at this one right away, I see it's an odd function, which usually starts low and ends high, but the lead coefficient is negative. So that means it's actually going to start up high and end down low. I see that it's got that plus 108. That's our y-intercept. So we could just make a 108 up here. Boom. We got a free dot. We do have to factor the rest to find the other zeros, though. So anytime our lead coefficient is negative, we'll take that out. Also, all these are divisible by 2. So that's give us x to the third plus 6x squared minus 9x minus 54. And then if we factor that by grouping, on the left there they have an x squared in common, x plus 6. Here we could factor out a -9, which leaves us another x plus 6. All right, so we got the -2 out in front. We've got x squared minus 9, which we're still going to have to factor. And then we have the x plus 6. All right, last thing is that x squared minus 9 is a difference of squares. So that would factor to x plus 3 times x minus 3. And then we also have the x plus 6. Whew! All of that. Now again, nothing is squared, so everything has a multiplicity of 1, which means when it hits those points, it just crosses straight through. There's no bend, there's no hit it and turn around. So we'll have a 0 at -3, +3, and -6. So I got to make sure my x's cover at least these numbers. So I'll go to -6, 1, 2, 3, 4, 5, 6. And we'll go to +6, 1, 2, 3, 4, 5, 6. All right, we have zeros at -3, +3, and -6. Remember, we also have to hit that y-intercept up at 108, and we have to start high and end low. Now, my arrow that I indicated over here, that's a little far over here. So let's see what we got. We're starting high. We're going through this point. Whee! Through that 108, and then through that 3. Beautiful! That graph looks a lot nicer than our previous one. But that's it, man. That's it. Let's try one more, and then I want you to try one. Example 4, part 2. Here's where we got some multiplicity. Now, if you look This is an odd function because it's x to the fifth. That means start low, end high. And it's a positive lead coefficient. So we can keep that in the back of our mind. It's going to start low, end high. We'll keep that in mind. All right, any common factor? Oh yeah, they got x to the third. Once we factor that out, we're left with x squared plus 6x plus 9. This looks pretty familiar. It looks like our earlier problem. X squared plus 6x plus 9, factors of 9 that add up to 6 would be 3 and 3. So we would write that as x plus 3 squared. All right. So remember, if there's an x on the outside, even if there was a 7 in front of it, it's still going to come out to 0. This x plus 3 would be negative 3. And then the multiplicity, finally. So x to the third means that 0 is going to have a multiplicity of 3. And we'll talk about that in a minute. This x plus 3 is to the second, so it has a multiplicity of 2. So now we're going to graph it. Our x we have to include at least to negative 3. And that's it. We don't even need positive stuff. But we'll put up to 3. We'll keep it balanced. And the y-intercept here, there's no number that doesn't have an x. So it's going to cross right at 0. That's going to be our y-intercept. So look, our two zeros are at 0 and negative 3. So we know we're starting low, we're ending high, and we need to go through those 2 points. Here we go, guys. We're starting low. At negative 3, it has a multiplicity of 2. So that means it's going to hit that point and then come back down. So we're going up. As soon as we hit that dot, oh, we're back down. Now, the 0 has a multiplicity of 3. So it's not just going to cross through. It's going to cross, but it's going to have a bend in it. So it might look something like this, like, woo! Look at that. Gorgeous. Starts low, ends high. This has an even multiplicity, so it hits it and turns around. This one has an odd multiplicity, greater than 1, so there's a bend through that point. I got one that I would like you to try. Here it is. Try your best, pause it, and actually check in with your work here. Even function, starts high, ends high. So let's see, at negative 3 it has a multiplicity of 1, so it's just going to cross through there. At 0 it has a multiplicity of 4, so that means it's going to hit 0 and then turn around. And then at 2 it has a multiplicity of 1, so it just crosses right through it. We did it! We're having fun! I think there might be like a sum up thing here. Oh, there's 2 for you to try? My goodness. Forgot about this one. All right. X to the fourth minus 26x squared plus 25 equals 0. So factors of 25 that add up to 26 would be 1 and 25. So x squared minus 1, x squared minus 25. Those are both differences of squares. X plus 1 times x minus 1, x plus 5 times x minus 5. Nothing repeats, nothing is squared or cubed, so everything has a multiplicity of 1, which means it just crosses through at these points. -1, +1, -5, +5. The y-intercept will be 25. 25. Let's see, we got to include -5, 1, 2, 3, 4, 5. Up to 5, 1, 2, 3, 4, 5. All right, we got zeros at -1, +1, -5, +5, and a y-intercept at 25. It's even and positive lead coefficient, so that means it starts high and ends high. And everything has a multiplicity of 1, so it just crosses through. Woo! Wee! Woo! All right! Fun! Now, before I say that's the end of the video, let's check the next slide here. That might be it. All right. How real zeros are represented. On a graph, they're your x-intercepts. Count the number of x-intercepts. Look for multiplicity. So, this has a multiplicity of 1. This has a multiplicity of 1 because it just crosses through. Every time it crosses through, that's 1. So here it'd be like 1, 2, 3. And then on 1, it hits it and turns around. So that would show a multiplicity of 2. Now, if you add up all those zeros, again, if it crosses through, it's 1. If it hits it and turns around, it's 2. And then if there's a bend through it, we say that's 3. So this would be 1, 2, 3, 4, 5. This is a 5th degree polynomial. Oh, yeah, it's over here. And an equation, factor and solve. There it is. So here it is in factored form. This x on the outside would equal 0. X minus 1 would equal +1. X plus 2 would be -2. X plus 1 would be -1. The one that has a multiplicity of 2 would be the x minus 1 because it's squared. Which again, if you look at that point on the graph, that's where it hits it and turns around. So that would show the even multiplicity. It's easier to see multiplicity in factored form rather than a graph, because technically that could be something squared or it could be something to the 8th power, right? Because if it's even, it hits it and turns around. So you can't really tell. And that's it.